Hi, I'm Nathan Perkins, and today I'm going to be talking to you about the string theory. Many of you may know matter is made up of atoms, and atoms are made up of protons, electrons, and neutrons. Protons and neutrons are made up of what's called quarks, and electrons, quarks, and what are called neutrinos are called fundamental particles and cannot be broken down further. The problem with these is that there's over a dozen different fundamental particles, and it's like having a dozen different building materials for a house. It doesn't really work very well. And there's two different theories that explain motion in the universe: general relativity, which is big objects that show stability of the universe, and quantum mechanics, as described in de Souza's and Iyengar's article, as basic small particles that show unpredictable, jumpy views on the universe. And you can't have a universe that with two different sets of rules, which is described in Chen and Kuji's article, The Rising Landscape, a visual exploration of superstring revolution in physics. And the solution is what's called the unifying theory. And one of such theories is the string theory, which says everything is made up of vibrating things called strings. Different vibrations make up different particles, which is not a problem because the fundamental building material it is a fundamental building material that can take on multiple forms. This resolves the problem with general relativity and quantum mechanics. The string theory is the unifying theory. That's the what, and here's the how. How does the string theory work? So the main thing about string theory is dimensions. The fundamental direction of dimensions is like x, y, and z on a graph that we know. So to make this easier, let's start from the ground up. Whenever you have, hopefully you can see this, maybe not, I'll draw it bigger. You can have a point, and that takes up one dimension, or it is 0 dimensions, and it has no direction. It takes up 0 space. It's just a point. And if we were to drag that point, that makes a line. And a line is one dimension, and it has one direction. It has 0 amount of width and 0 amount of height, but it has length. And if we were to make that into a plane, we just drag this line down, and that is to make a plane. And that has no height, but it has length and width. And then to make that a volume, you have a plane, and you just drag the plane up, and that makes a volume. And this marker is terrible, but that makes a volume. And then you're probably wondering, how do I make 4 dimensions? Which way do I drag it? Which way do I drag a volume to make 4 dimensions? And you can't really drag a volume, because once you drag a volume, it just becomes another volume. And most physicists think of the first 3 dimensions as spatial dimensions, as you will find out in a second, because the 4th dimension is not a spatial dimension. It is actually time. Dragging something through time, can take different effects on things, and so time is widely thought of as a dimension. And I say widely because the string theory is just that. It's a theory. It's not a law. So the 4th dimension is thought of as time. And the best way to visualize time is to go back to 2-dimension, what I call the flatland. It's just a plane, and to visualize time, you put an axis right here, and you know, this is our rectangle, and it slowly changes over time as it spirals up this axis all the way. And that's the best way to visualize 4 dimensions, or dimension as or time as a dimension. You know, 4 dimensions is fairly easy to handle with our brains, but the string theory doesn't just work in 4 dimensions. The string theory actually contains the complement in Levat's article. He says the string theory is contained as contains a complicating 11 dimensions. And you know, how do we fit 11 dimensions on the graph? And that's kind of difficult to perceive, but you know, it would be like just you have your x, y, z, and then you have like 7 other dimensions that come out from that. That's the best way to visualize 11 dimensions. And you know, if you imagine 11 dimensions, or if you want to try to imagine 11 dimensions, you can think of an ant walking on a line, which is 1 dimension. And you know, this ant, you may think that it can only walk one way, one direction, but you're wrong, because the ant can circle around clockwise, it can circle around counterclockwise around the line, and you might be thinking, you know, you're thinking in 3 dimensions, but 11 dimensions, or the string theory, says that every dimension, or there's an extra dimension at every point in space and time. So, you know, we can only see and perceive 3 dimensions because, well, they're curled up so small that we can't perceive them. The other 11 dimensions are curled up into one space called a Calabi-Yau manifold. And within these manifolds, strings vibrate in every dimension. And, you know, that's as deep as I can go into generalizing the string theory in this allotted time, but thank you for listening. That's all I have.